Hello, my name is Professor Johnson, and today we will talk about the central limit theorem for means. Central limit theorem is usually denoted in books as CLT, central limit theorem. Now, I'm going to give some quick theory to show you where some of these numbers or formulas come from. We will start with a population. A population represents all that we are interested in. Now, we will have a known mean and a known standard deviation. Okay, known mu, no sigma. It'll be given to us from the population. Now, the population we could denote as like a big X. And the distribution may be unknown. Now, it is possible that you do have a known distribution. It could be uniform, exponential, it could be normal. But we're not interested in that. We are interested in sampling. So what we're going to do is take a sample, and we'll have a sample size n coming from the population. Now, what the central limit theorem tells us is if we sample many times, so I'm going to take a sample many times from this population. I'm going to keep sampling over and over. As n gets larger and we calculate every single sample's mean, if we can't calculate the sample mean for each of these samples and we lump them all together, everything becomes distributed normally. So what ends up happening is that you have X bar is distributed normally, and if you think of sample means, what happens is the mu stays the same, but the standard deviation actually gets smaller. Everything shrinks closer to that true mean. And the standard deviation would be sigma over square root of n. So you'll have to do a little bit of calculating when finding standard deviation for sample means. Okay, so that's just the brief breakdown of the theory. We will be using this primarily in our example. So let's read our example. Suppose the number of hours worked in a single week by Victoria College students has an unknown distribution with mean 8.5 and standard deviation 4 hours. Suppose we randomly select 40 students on campus and find the mean. So notice, we are starting with an unknown distribution. The population would be all Victoria College students, right? Victoria College students, that is our population that we're thinking of. And from that population, we know the mean, 8.5 hours, and we know the standard deviation, 4 hours. Now, what we want to do is think of the central limit theorem for means. The central limit theorem for means tells us exactly what we just discussed a little bit ago. Tells us that X bar is distributed normally. Okay, so now we're working with a normal distribution. We come from an unknown distribution, but if you sample many times, as n becomes larger, it will end up approaching a normal distribution curve. All right, so let's answer question 1. What is the mean for the sample mean distribution? So the mean for the sample mean distribution. The sample mean distribution is exactly this guy right there, X bar. That X bar represents the sample mean distribution. This is distributed normally, and what we know with central limit theorem for means is the mean stays the same as the population mean. And the population was Victoria College students, and that mean was 8.5. So 8.5 hours will be our mean. It stays the same. Okay, but what changes, and we talked about this a little bit in the theory, the standard deviation changes and it gets smaller actually. The standard deviation for the sample mean distribution, right, X bar, we know X bar is distributed normally. You have to recall that we have sigma divided by the square root of n. Okay, now sigma, that represents the standard deviation. So that would be 4 from the unknown distribution, or from our population. And then we have to divide by the square root of n. Now, n is our sample size. So suppose we randomly select 40 students on campus and find the mean. So we did 40 students. We got 40. So that will go right here, the square root of 40 in our denominator. Okay, now if we approximate this, we could put that in our calculator. We could do 4 divided by square root of 40, and it's about 0.632. But I didn't ask you to round or anything, so we could round that to 3 decimal places or whatever. But what I'm most interested in is finding probabilities. And to find probabilities, we are going to use the idea of normal distributions. So here is our first question with probability. What is the probability that the sample mean is less than 8 hours worked in a single week? Round to the thousandths place. So now we're dealing with this idea of probability. Do you remember how to find the probability with a normal distribution? And we will use the calculator. So if you've thought about it a little bit, now we want to use what's called normal CDF in your calculator. Normal CDF always goes in this pattern: lower, upper bound, upper bound, comma, then you have your mean, and then you have your standard deviation. I'll just denote it like that. So we need to put the mean and the standard deviation. Now, we want probability that the sample mean is less than 8 hours. So we are thinking sample mean is x bar. Now we know from before x bar is distributed normally, which is why we can use normal CDF. This will be equal to, let me write the probability notation first. The probability that the sample mean, so x bar, is less than 8. This will be normal CDF. Now I want to think of the lower bound. I'm going to the left. You think if you look at the less than 8, you're going towards the left. So as far left as you can go would be -1e99. The upper bound would be the highest you could go, which is a value of 8. And then the mean comes from the sample means distribution, which comes from question 1, is 8.5. And then the standard deviation is actually what we found in question number 2. The standard deviation for the sample mean would be 4 divided by the square root of 40. And you can actually type that in directly to the calculator in that way. Now, do you recall how to get to the normal CDF button in your calculator? You should go second vars, and it's number 2. Now, if you have the 83, you know that you have to type it in with commas, just as I did written out here. If you have the 84 plus, you will have the menu. Now, the lower bound, we have the upper bound. Mu stayed the same at 8.5. The standard deviation changed, though, to 4 divided by square root of 40. Now, when you hit enter, you will see that it listed it out just like I wrote out here. If I go all the way to the left, you can see that. Normal CDF, so lower bound, you type it right in. Comma is right above 7 if you had to type it in using commas. 8, 8.5, comma, 4 divided by square root of 40. Now, I also wrote it in as 4 divided by the square root of 40 because you saw in question 2 that it's kind of a funny decimal. And if you round too early, rounding too early will cause errors in your final calculation. So I do not want to round too early. That's why I typed it in exactly that way. Now the thousandths place, that would be 3 decimal places. That's because the first place would be tens, goes tens, hundreds, thousands, and then so on. So we want the thousands place. That 5 right there would bump up that 4. So our final answer would be equals 0.215. All right? So there's our first central limit theorem probability worked out. To recap, we know we're looking at sample means, so x bar. X bar is distributed normally by the central limit theorem for means. And the central limit theorem for means tells us that the sample means distribution's mean will be 8.5, and the standard deviation's sample mean distribution will be the standard deviation from the population divided by the square root of your sample size. Okay, so let's think about this next one. What is the probability that the sample mean, keywords, is between 10 hours and 13 hours worked in a single week? Round to the thousandths place again. So we're thinking of probability of something, and we need to be between 10 and 13. And what's between there? Between 10 and 13 is the sample mean, so x bar. So you see how I wrote out that notation? The probability that x bar is between 10 and 13 hours. We know that x bar is distributed normally. So this will be equivalent to using normal CDF. The lower bound would be 10. The upper bound would be 13. The mean remains the same at 8.5. And the standard deviation, we know for sample means, has to be adjusted. It actually truly gets smaller. You take 4 and divide it by the square root of 40, which we did earlier. Now, remember, if you look over here on the calculator, 0.632, if you put that in that spot, you'd get close to the same answer, but your rounding might be off by a few decimal places. So make sure you type in the full value so that you don't lose accuracy with your rounding. Okay, so let's go back to the calculator, type it back in, go second vars, number 2. Now, in this case, the lower bound, we have 10, upper bound, 13, mu, 8.5, and standard deviation, 4 divided by square root of 40. Now, if you have the 84 plus, as you can see, you have a little bit of an advantage because it remembers what you just typed in. So if you have 2 questions in a row that are similar, it remembers things. Okay, hit enter, and we want to round to the thousandths place. So let's look, tens, hundreds, thousands. The thousandths place would actually also be bumped up to 0.009. That would be our final solution. Thank you for watching the video.